This is Lecture 6, Foundations of Statistical Inference. By the end of this lecture, you should be able to calculate and interpret a variable standard deviation, understand why it is difficult to make inferences from one sample, calculate and interpret a confidence interval around the mean of a sample distribution, calculate and interpret a confidence interval around a sample proportion, and be familiar with commonly used Greek symbols in statistics. In the last couple of lectures, I showed you how to use simple statistics to describe data and analyze the relationship between two variables. In this lecture, I will review advanced statistical techniques to describe data. And for the rest of the course, I will review more advanced statistical techniques to analyze the relationship between two variables. Before moving forward in discussing how to use advanced statistical techniques to describe data, I want to review simple ways to describe data that you've already been introduced to. Recall that when describing data, there are three measures of central tendency that could describe the typical case of a variable. The mode tells us the most repeated value in a variable. The median tells us the center value when observations are ordered from the smallest value to the largest value. And the mean is the arithmetic average, where we add all the values together and divide the sum by the total number of observations. And when we describe how a variable is distributed in a bar graph or histogram, we describe its center, its spread, the number of peaks, and the skewness. The center is just the median. The spread is the largest value minus the smallest value. The number of peaks is the number of peaks in the graph. And the skewness tells us whether the bar graph or histogram is symmetrical or not, or whether both halves of the graph mirror one another or not. In the next 5 slides, I'm going to review the examples I gave you on how to use center, spread, modality, and skewness to describe bar graphs and histograms. In this graph, the center is 50, which I calculated. The spread is 90, the largest value, minus 10, the smallest value, which equals 80. The graph is unimodal with one mode of 50, and there is no skew as the left and right sides of the graph extend about the same amount from the center of the graph. In this graph, the center is 50, the spread is 100, the largest value, minus 0, the smallest value, which equals 100. The graph is bimodal with one mode at 50 and one mode at 100. The peaks are even. And there is no skew as the left and right sides of the graph extend about the same from the center of the graph. In this graph, the center is 50, the spread is 100, the largest value, minus 0, the smallest value, which equals 100. The graph is bimodal with one mode at 0 and the other mode at 100. The peaks are not even. The 0 peak is the larger mode. And there is no skew as the left and right sides of the graph extend about the same amount from the center of the graph. In this graph, the center is 50, the spread is 70, the largest value, minus negative 10, the smallest value, which equals 80. The graph is unimodal with one mode at about 50. In this graph, there is a negative skew as the left side of the graph extends much further than the right side of the graph. In this graph, the center is 20, the spread is 70, the largest value, minus 10, the smallest value, which equals 60. The graph is unimodal with one mode at 10. And in this graph, there's a positive skew as the right side of the graph extends much further than the left side of the graph. Now I'm going to teach you an additional way to describe the distribution of a variable, the variance and standard deviation. Consider these two histograms of two different variables. Each variable has the same mean, 50, and each variable has the same spread, 100 minus 0, which is 100, and each graph has one peak. They're unimodal around 50, and each one has no skew. Yet, the variables still look distributed in different ways. If you examine the variable on the left, the distribution is more peaked around the mean of 50, meaning many observations take values that are close to 50. But with the variable on the right, the distribution is more flat, with many observations taking values that are far away from 50. On the left, we would say there's very little variance, and on the right, we would say there's a lot of variance. We can calculate two numerical values that tell us by how much a variable's observations deviate from its mean on average. Those values are called the variance and standard deviation. I will show you how to calculate them. First, the sample variance, denoted by an S squared, is the sum of each observation minus the sample mean squared, and that value divided by the total number of observations minus 1. Second, the sample standard deviation, denoted by the letter S, is the square root of the sample variance. In order to show you how to calculate the sample variance and sample standard deviation, I will use a variable called percent living below $2 per day. There will be 10 observations from less developed countries. In order to calculate the sample variance, you start by taking the sample mean of your data. Recall that the mean is just the average of all the cases. So let's say we collected data on the percent of people living under $2 a day in 10 countries. The overall mean of this data was 29.4. Then you subtract the mean, in this case 29.4, from each observation. So for country 1, you calculate 46.1 minus 29.4, which equals 16.7. For country 2, you calculate 60.4 minus 29.4, which equals 31. And you continue this process for each observation. Note that all we are doing right now is calculating how far each individual observation deviates from the mean of 29.4. Next, you take the values from step 2 and square them. So the calculation for the first observation would be 16.7 squared, which equals 278.9, and the calculation for the second observation would be 31 squared, or 961, and you continue this process for each observation. Note that we square the values to get rid of negative deviations. It is impossible for an observation to negatively deviate from its mean. Next, you add all the values from step 3 together. In this case, the value was 5,840.4. Then you take the value from step 4 and divide it by the number of observations minus 1. In this case, the number of observations was 10, so 10 minus 1 is 9. So the calculation is 5,840.4 divided by 9, which equals 648.9. So the variance for the percent living under $2 a day sample is 648.9. Note that all we are doing here is calculating the average deviation from the mean. We added all the deviations together and divided by the total number of observations minus 1, which is almost like calculating an average. Last, you take the square root of the variance to find the sample standard deviation. We take the square root because we squared the values in step 3. As a result, the values of the variable became much larger, so you want to take the square root to bring the number back to a more realistic level. In this case, the square root of 648.9 is 25.5. So our sample standard deviation for percent living under $2 a day is 25.5. Now we can interpret the mean and standard deviation. To interpret, you should start by stating the mean of the variable. Then you would say, in our sample, observations deviated about standard deviation units from the mean on average. So applying this to our example, we would say, on average, 29.4% of people in less developed countries live below $2 a day. However, in our sample, observations varied about 25.5% from the mean on average. Note that I only use these percentage signs because the variable is measured in percentages. Use whichever units the variable is measured in. Now I'm going to talk to you about the differences between population statistics and sample statistics. A variable's population is the entire universes of cases that we could potentially collect data on. But normally we do not work with populations. It would be impossible to identify every single potential case to collect data on. Instead, we normally work with samples, which are a subset of the population. When we work with samples, we make inferences from our samples and apply them to the entire population of cases. So for example, we might collect data on the number of protests and democracies throughout the world in a year, but only examine 20 democracies. We'd assume that the average number of protests in a year in those 20 democracies would be close to the average number of protests and democracies per year in the entire world. However, this could be a problem if our sample statistics do not accurately reflect the true population statistics. Here is a real-world example of how applying sample statistics to an entire population could be a problem. Imagine I collected data on the percent of people living below $2 a day in less developed countries. In all, there were 124 less developed countries. After I collected this data, I found the population mean, denoted by the Greek symbol mu for this variable, which was 34.8%. So on average, 34.8% of people in less developed countries live below $2 a day. Now imagine that instead of collecting data on all cases, I took a random sample of 10 countries. For the sample mean, denoted by X bar, was 29.4. Based on this data, I would conclude that 29.4% of people in less developed countries live below $2 a day. Clearly, this value is not reflective of the true population mean of 34.8. So our sample estimate has some error. In order to illustrate how far off a sample mean can be, I created 10 random samples from the data set of the 124 less developed countries. The averages for the percent living below $2 a day variable ranged from 19.6% to 46.7%. As you can see, different samples can lead you to draw different conclusions about the true population mean. Clearly, these values are often not perfectly reflective of the true population mean of 34.8%. So, once again, sample means often do not equal population means. This is a problem since we use sample means to make conclusions about population means. This is also a problem for estimating the standard deviation of a variable. The population standard deviation will always be smaller than the sample standard deviation. To illustrate this point, here are the statistics from the population living under $2 a day example. The population standard deviation sigma was 24. I calculated this value on my own. You do not need to know how to do this. The sample standard deviation S was 25.5. Because we know our sample means will not always perfectly reflect our population mean, instead of just calculating a mean, we could instead calculate a range of potential means. We can do this by calculating a confidence interval around our mean. It tells us the range of potential population means from the smallest to the highest values. But before I teach you how to calculate a confidence interval, I need to discuss how we know we can confidently estimate a range of potential means of a population mean from a sample. We can do this because of something called the central limit theorem. The central limit theorem tells us that if we collect an infinite amount of samples, let's say we take an infinite amount of samples of 1,000 observations each, 95% of the time, the sample means from each of those samples will be very close to the true population mean. This is because the distribution of sample means is normally distributed. So just for a visual representation, here's a picture of a potential distribution of sample means. Imagine that this is the true mean here. 95% of the time, when I take a sample of 1,000 observations, the mean of the sample will be within 2 standard units of the population mean. So even though our sample mean often will not reflect the true population mean, the sample mean will be close to the true population mean. Before I move on, I would like to talk a little bit about normal distributions. Normal distributions have one mode, so they're unimodal, and they are shaped like a bell. Normal distributions are symmetrical, meaning that if you fold them in half, each half would have the same exact shape. In other words, they have no skew. In addition, the center of a normal distribution is the mean, median, and mode of the distribution. Next, 68% of the values of a normal distribution are within 1 standard unit from the mean. 95% of the values of a normal distribution are within 2 standard units of the mean, and 99% of the values of a normal distribution are within 3 standard units of the mean. Standard units take into account the standard deviation and the sample size, which we will talk about soon. These characteristics mean that 68% of the time, a sample mean will be within plus or minus 1 standard unit of the true population mean, and 95% of the time, a sample mean should be within plus or minus 2 standard units of the true population mean, and 99% of the time, a sample mean should be within plus or minus 3 standard units of the true population mean. Using the concepts of the central limit theorem and the normal curve, statisticians developed 2 hypothetical distributions to use in statistical analyses, the z distribution and the t distribution. The z distribution is a hypothetical normal curve that has a mean of 0 and a standard deviation of 1. You can take the values of a variable and mathematically transform them into z-scores. This allows us to analyze variables with small values, such as in tens, or variables with large values, such as in millions, on the same scale. I'm not going to teach you the equations necessary to transform the values of a variable onto the z distribution. However, I will tell you that whenever you do take a variable's values and transform them into a z-score, the calculation for the mean of the variable will always result in a value of 0, and the calculation for the standard deviation of the variable will always result in a value of 1. This is because the z distribution has a mean of 0 and a standard deviation of 1. In addition, recall that the z distribution is a normal distribution, so 68% of the values are within 1 standard unit of the mean, 95% of the values are within 2 standard units from the mean, and 99.7% of the values are within 3 standard units from the mean. Although the z distribution is a useful tool, it does not take into account that some samples are small and some samples are large. With smaller samples, we have less confidence in our data because there's less information. With larger samples, we have more confidence in our data because there's more information. The t distribution allows us to take into account differences in sample size when analyzing our data. The t distribution is actually a set of distributions that account for sample size. The smaller the sample size, the larger the variance is in the t distribution. The larger the sample size, the smaller the variance is in a t distribution. Here is a visual representation of t distribution. The z distribution has the smallest variance, so 95% of the time observations are really close to the mean. The t distribution for a sample size of less than 30 has a large variance. So 95% of the time, the observations are quite far from the mean. And the t distribution for a sample size of 30, the variance is moderate. So 95% of the time, the observations are somewhat close to the mean. Now I'm going to show you how to use the t distribution to estimate a population mean. To do this, we calculate a 95% confidence interval around a sample mean. The confidence interval allows us to make a low estimate of our mean and a high estimate of our mean. I will use the following data to demonstrate how to calculate a confidence interval for a sample mean. Imagine I collected data on the percent of people living below $2 a day in 10 less developed countries. The first step in calculating a confidence interval is to calculate the sample mean of the data. The mean of the data was 29.4. Next, you calculate the standard error of the sample mean. To do this, you take the sample standard deviation, which I showed you how to calculate earlier in the lecture, and divide the value by the square root of the number of observations. The sample standard deviation of this data set was 25.5 and the number of observations was 10. So 25.5 divided by the square root of 10 is 8.1. Next, we have to calculate something called the degrees of freedom. The degrees of freedom is the number of observations in our data set minus 1. So we had 10 observations. 10 minus 1 is 9. So we use our degrees of freedom to find the value from the t-table that we will use to calculate the confidence interval. You can find a t-table on page 148 in your textbook. On the left-hand column is your degrees of freedom rows. There you will find the row that corresponds to the value of your degrees of freedom. If the value is not listed, you should choose the closest lowest number. After you choose the right row, you must find the right column. The column headings tell you the percentage of cases under the top portion of the t-distribution curve. So for the 0.05 column, it is 0.05 or 5% in the upper part of the curve. Although the table only focuses on the top of the curve, we want to know the area under both ends of the curve because we are calculating a lower bound of a confidence interval and an upper bound. That also means that if we are examining the area under the top and bottom of the curve, we would have 0.05 in the upper half and 0.05 in the lower half. If we added 0.05 and 0.05 together, we have a total of 0.10 under the entire curve. So if we want a 95% confidence interval, we want 0.05 under the curve. To do this, we would want to look at the 0.025 column, as it indicates 0.025 in the upper half of the curve and 0.025 in the lower half of the curve, for a total of 0.05 under the entire curve. So we will use the 0.025 column and the 9 row. The t-value that corresponds to 0.025 column and 9 row is 2.262. Note that from this point forward, you will always be required to use the 0.025 column for confidence intervals. So you should just make a note somewhere to use the 0.025 column for confidence intervals. Now we have all the information we need to calculate our confidence interval. The lower bound of the confidence interval is the sample mean minus the t-value times the standard error. In this case, the calculation would be 29.4 minus 2.262 times 8.1 for a value of 11.1. The upper bound of the confidence interval is the sample mean plus the t-value times the standard error. In this case, the calculation would be 29.4 plus 2.262 times 8.1 for a value of 47.7. Now that we are finished calculating the confidence interval, we can interpret it. We would say that we have 95% confidence that the true mean of our variable lies between the lower and upper bound that we calculated. Or applying it to our example, we would say we have 95% confidence that the true mean of our variable lies between 11.1 and 47.7. We could also say we have 95% confidence that the true mean of our variable is the mean of the variable plus or minus the t-value times the standard error. Or we could say we have 95% confidence that the true mean of our variable is 29.4 plus or minus 18.3. Now I'm going to talk to you about a special topic, proportions. We have not worked with proportions yet. With a proportion, we want to know how many cases in a variable fit into a category of that variable as compared to all the cases in a variable. We normally use proportions when we use survey data. For example, if we collected data on the number of people who supported two different candidates, we'd be working with proportions. There would be two categories of the variable, one category for respondents who support candidate 1 and one candidate for respondents who support candidate 2. Imagine there were 100 respondents and 52 of them that said they supported candidate 1 and 48 said they supported candidate 2. This is how you would calculate the proportions for each category for this variable. The calculation for the proportion P is the number of cases in a category divided by the total number of cases. So in this example, 52 respondents said they supported candidate 1 and there were 100 total respondents, so 52 divided by 100 is 0.52. We also have to calculate a value Q, which is the number of respondents who did not support candidate 1. The calculation for Q is simply 1 minus P, or 1 minus 0.52, which is 0.48. While this is interesting information, just like the example from our sample mean, the sample proportion might not accurately reflect the true population proportion. As such, we can also calculate a confidence interval around a proportion. To demonstrate how to calculate a confidence interval around a proportion, I will use the following example. Imagine we collected data on how many people support candidate 1 versus candidate 2. We had 100 respondents and 52 supported candidate 1 and 48 supported candidate 2. We want to make an estimate of how many people support candidate 1. First, we would calculate the proportion for individuals who supported candidate 1. The calculation for the proportion P is the number of cases in a category divided by the total number of cases. So in this example, 52 respondents said they supported candidate 1, and there were 100 total respondents, so 52 divided by 100 is 0.52. We also have to calculate a value Q, which is the number of respondents who did not support candidate 1. The calculation for Q is simply 1 minus P, or 1 minus 0.52, which is 0.48. Next, we have to calculate the standard error of the sample proportion. The standard error of the sample proportion is the square root of P times Q, and that value divided by the square root of the number of observations. So in this case, the standard error of the sample proportion is the square root of 0.52 times 0.48, and that value divided by the square root of 100, which is 0.05. Next, we have to calculate the degrees of freedom to find our t-statistic. Recall that the degrees of freedom is the number of observations minus 1. So in this case, we had 100 observations, so 100 minus 1 is 99. Going to table 6.4 in your textbook, we have to look for a 99 row. There is no 99 row, so you look for the closest lowest one, which is 90. Then we look at the 0.025 column since we want a 95% confidence interval. The t-value associated with the 90 row and the 0.025 column is 1.987. Now we have all the information we need to calculate the lower bound of our confidence interval. The calculation is the proportion minus t times the standard error. So in this case, the calculation would be 0.52 minus 1.987 times 0.05, or 0.42. Next, we calculate the upper bound. The calculation is the proportion plus t times the standard error. So in this case, the calculation would be 0.52 plus 1.987 times 0.05, or 0.62. Now that we have calculated our confidence intervals, we can interpret them. We can say that we have 95% confidence that the true proportion is between the lower and upper bound. Or applying it to our example, we could say that we have 95% confidence that the true proportion of people who support candidate 1 is between 0.42 and 0.62. Alternatively, we can say we have 95% confidence that the true proportion is P plus or minus t times the standard error. Or applying it to our example, we could say we have 95% confidence that the true proportion of people who support candidate 1 is 0.52 plus or minus 1.987 times 0.05, or 0.52 plus or minus 0.1.